Alright, the title of this talk is Calculus Isn't So Scary. And the reason that's the title is because I get a lot of scared Calculus 1 students in my office. And most of the time the reason that they're there is because of this formula that I'm going to write down right here. Okay, so admittedly that is pretty scary, but like most equations in math, it looks a lot worse than it is. This right here is called the definition of a derivative. A derivative is a really fundamental concept to calculus. It's really one of two fundamental concepts in calculus, derivatives and integrals. Derivatives are focused on really through the entire Calculus 1 class. So hopefully by the end of class you'll have a little bit of understanding of where this equation comes from, and it won't be too scary. But first, I want to talk a little bit about why we're talking about derivatives at all. The first thing to understand is that a derivative is a rate of change. I'm going to write that down. I know that that's not a totally clear sentence, so I want to go through a couple of examples of what it means to be a rate of change. As I'm going through these examples, please keep your ears open for the word change. I'm going to use it a whole lot in these examples. Here we go. Example number 1 is going to be a petri dish. So here's your petri dish, and inside a petri dish you have some bacteria growing. Now this doesn't have to be a petri dish in a biology lab. It can also be your smelly socks, or if you're like me, a banana that's probably hidden under your car seat. Just something that has bacteria growing on it or in it. You might be interested in what the population of that bacteria is, so I'm going to give it a name. I'm going to call it P. The population inside this petri dish is definitely changing. So what we can say is this. We can say that the rate of change, or how fast the population is increasing, is the derivative of P. Now I'm going to write that down. So if you wanted to write down a model so that you could predict the population of the bacteria in this petri dish, you would definitely be using a derivative in that model. Any further explanation is going to have to wait for another time. Let's go on to example 2. Example 2 is going to be money related. Let's say you own a t-shirt business and you've calculated that your profits are going to look something like this. So on this axis would be how much money you make, and along this axis is going to be, we'll say, how many t-shirts you produce. Now your graph of your profits here, sometimes we'll call that a function. We'll just name that thing P as well. Now your profits, if you look at this graph, are clearly changing. There's that word again, change. So we have a derivative here. Anytime your profits are increasing, as they are right here where I'm pointing, we call that a positive derivative. Now anywhere over here, your profits are actually decreasing. That's a negative change in profit, so we call that a negative derivative. And right here in the middle is where you're going to make your most money, and a lot of people want to find that point. Now this point actually occurs when the derivative, or change in your profits, goes from positive to negative. And that's something the derivative can do for you. I'm going to write that down. So there it is. You can find your maximum profits using derivatives. So those were just two examples of how we could use derivatives. And in reality, we use derivatives all of the time. Anytime anything moves or changes, a derivative is involved. So because we don't have a lot of time, I'm going to stop right there. Hopefully that gives you an idea of why we talk about derivatives at all. Now in class, we're going to talk about how do we find this formula right here. All right, I'll see you in class.